A little bit about trig. Did you learn like about SOHCAHTOA? Mm-hmm. Have you ever heard of this definition that it's just an acronym to help you remember, but that the sine of an angle is equal to the opposite side in a triangle over the hypotenuse. The cosine of an angle is equal to the adjacent side over the hypotenuse. This is a right triangle as well. And the tangent of an angle is equal to the opposite over the adjacent. Have you seen that before?
Mm-hmm. I saw something different.
Just something different? What did you see?
It was like Oscar had a hold on Arthur or something like that.
So it was another acronym, but it did the same thing, right? Yeah. And so the thing about this approach is that if you have a right triangle, and this is your angle or the thing that you're finding the sine, cosine, and tangent of, that angle can only be between 0 and 90. Does that make sense? Because once it gets above 90, it's no longer a right triangle because you've got two angles that are both 90 would add to 180, which is too big to be a triangle, right? So we'll talk about how to generalize that and make a function that's a sine function and cosine function and tangent function where you can do all numbers, not just angles that are in that restricted range. Okay? So, and there are two measurement systems for angles. The one that you're probably most familiar with is degrees, right? There's another system called radians. Did anybody learn about radians in school? A little bit? Okay. So this trigonometry depends on the concept of this angle. So this angle is formed when you rotate a ray. So you have this thing called the initial side around some endpoint, and how far it rotates is the angle. Usually it's represented by the Greek letter theta. So, and for some reason, don't ask me why because I'm not 100% certain, these rotations are always taken counterclockwise. In this system, counterclockwise is positive. So they're all taken counterclockwise. So counterclockwise is the default or positive direction. So a counterclockwise, we're still recording, okay, counterclockwise rotation produces a positive angle. And then if that direction is positive, the other direction is a negative angle. So a clockwise rotation, that makes a negative angle. So are angles unique? Like if I give somebody one angle measure and give somebody some other angle measure, are they always going to be different angles? No. No. So like for example, I could give you 90, I could give you negative 270, and they're the same thing. Does that make sense? So two different angles may have the same initial and terminal sides. These angles are called coterminal, meaning they terminate in the same place. But it's something like one angle measured this way, that's your first theta 1, and one angle measured that way, that's your theta 2, and they are the same angle. There's an infinite number of ways to represent every single angle. You could also go around more than once, right? Rotate once and then 90, that would also be the same angle as 90 degrees. And angles are called, they're in standard position when you put their vertex at the origin and the initial side is along the x-axis. Okay, so my guess is you know most of the stuff that comes next. So how many degrees is one complete rotation?
360.
360. Okay, a straight angle. So a straight angle would look like there's your initial ray and you rotate around until you have a straight ray in the other direction. How many degrees is that?
180.
180. What's the measure of a right angle?
90.
90. How about acute?
Less than 90.
Measure less than 90. And obtuse technically is between 90 and 180. It's not strictly bigger than. This is what your book said. And if you're talking about degrees, you always put the little circle because if there is no symbol, that actually means you're in radians. So with degrees, always put like a little circle. and they're just two vocabulary words, you should know what they mean. Two angles are complementary if their sum is 90, and they're supplementary if their sum is 180. Okay, so now comes the slightly tricky part. Most applications in like engineering, they use degrees, but the definitions of the functions in math, they use this other system called radians. So it's just another way to define angles that works out a little bit nicer for certain things. So here is the technical definition of what a radian is. So if you've got a positive angle formed by a central angle, and it's got a measure of 1 radian, if the length of this arc opposite of the angle is equal to its radius. So here's what that looks like in a picture. So you have your initial ray, and you have this other ray, and that theta is equal to 1 radian, and I should have the theta here because theta really is the angle. If the length of that sort of part of a circle, which is called S, is equal to this R. So the idea is theta is equal to 1 radian if S equals R. And it doesn't actually matter how far out you take that little s to be. That if your angle is 1 radian, that s and r would be equal if you drew the little sector there, or if you drew the little sector here. So the technical definition of how you find the angle in radians is you take s over r, where s is the length of the arc and r is the length of that side. And there'll be a system that you can use to convert between the two. One thing that this lets you do pretty nicely is it lets you find areas, like area lengths of sides of a circle. Like since theta equals s over r, in that case s will equal theta times r. Does that make sense? Once you know what the radian measure is, you multiply by the radius, and it tells you how long this piece is. Okay? So, just a quick, easy example. So what is the radian measure if you have a central angle opposite an arc of 24 meters, and the circle has radius 6? So this picture is not going to be to scale, but the idea is you have some angle theta, this thing going around, the arc is 24 meters long, and this radius of that circle is 6. That is totally not drawn to scale, okay? But that's the idea. And the idea is the radian definition of what that angle is that theta is equal to s over r, where s is the length of the arc and r is the length of the radius. So in that case, what is this? What's s?
4.
The answer is 4, but what's s?
24.
24. What is r?
6.
And that would equal 4.
So I remember from somewhere that 1 radian was equal to 180 degrees.
That's not right. Yep. It's okay, but that's actually not right. It's pi radians equals 180 degrees.
Oh.
Yeah, so we're gonna do that. We're gonna do that next, okay? We'll get the conversion factors next, and I've got a goofy way to help you remember it. Well, it's only a little bit goofy, but. Okay, so using what is the radian measure of an angle that is 360, and how about 180? Because once we know this, we can convert any angles into each other. Like, and I'll teach you tricks to do this quickly. So, okay, so the definition of radian measure is that theta equals s over r. And if you have 360 degrees, what is s, or the length of that whole arc? Like if you start here and you go around the entire way at a distance of r, how far have you traversed? What's the circumference of a circle? 2 pi r. Does that make sense? Yeah? So S is equal to 2 pi r. So in that case, this theta is 2 pi r over r, which is what? 2 pi. So 2 pi radians is the same thing as 360 degrees. So what you have to do whenever you go skiing now, when you like do a 360 or anything else, you got to say, I just did a 2 pi. Oh, come on, it'll be more fun. So the thing is here, you can think going around the circle is 1 360 or 1 2 pi. It's the same idea. And that definition means that the r's don't matter. So that's what, and so if 2 pi is 360, how much is 1 pi?
180.
Yep. So if it's the whole thing to go around is 2 pi, halfway is 180, and half of 2 pi is, did I just say that wrong? I did. The whole way around is 360 or 2 pi, right? Halfway is 180 or 1 pi. So pi radians is equal to 180 degrees. Okay, so let's talk about this. If you go from, because conversion factors are tricky, if you go from inches into feet, what do you multiply? You have some number, say like 26 inches. How do you get that into feet?
Divide by 12.
You put the inches in the bottom, does that make sense? And the 1 foot goes in the top. It's called a conversion factor. Does that make sense? The reason you divide by 12 is you need these inch labels to cancel. Does that make sense? Yes, okay. So if you want to go from radians to degrees, what do you want to cancel? The radians. So you need your pi radians in the bottom. And what is pi radians equal to in degrees?
180.
180 degrees. Could I have used 360 and 2 pi? Why didn't I?
It reduces.
Because it reduces to pi over 180. Does that make sense? But the idea is that the thing you want to cancel has to go in the denominator. Does that make sense? That's the idea is going to come from chemistry if you're going to take chemistry. Who's taking chemistry? Or has to take chemistry, right? You do a lot of dimensional analysis, don't you? Yeah. So if you want to go from degrees to radians, what do you want to cancel there? Degrees. So the degrees goes in the bottom. And what goes in the top? So pi radians. And technically, multiplying by pi radians over 180 is multiplying by 1 because of the different labeling systems. Does that make sense? Those are equivalent measurements in different labeling systems. Okay, so those are the conversion factors. We'll do some using these, and then we'll also discuss some common ones that you can kind of just count out using various patterns and things. Okay, so 60 degrees. So we do 60 degrees times, do you do pi over 180 or 180 over pi? Pi over 180. And if you put no label, I'm going to assume that it's radians. Does that make sense? That's kind of the default label for angles. If it's degrees, you're going to need the circle. Now that's going to be 60 pi over 180. Can you reduce that fraction? Quite a lot, right? How many 60s are there in 180? 3. So that is pi over 3. And you can think to yourself, oh my gosh, I don't want to do that many of them. This is annoying. It's going to take forever. Is anybody thinking that right now? Not even a little bit? Is there an easy pattern you can use to get the rest of them? Yes! So notice how these are always increasing by 60, right? They gave you a very specific list of numbers. So, which means to go from 60 to 1, if 60 is 1 pi third, how many pi thirds is 120? 2/3. So 120 degrees is going to be the same thing as 2 pi thirds. 180, using that pattern, you could say, well, it's 3 pi thirds, and then what does that reduce to? Just pi, exactly, which should make sense, right? We said 180 is pi, yes? Okay. How about 240? How many pi thirds is that? 4 pi thirds, yep. Okay, 300 is how many pi thirds? 5 pi thirds. And then 360 is 2 pi, yep. But what they're trying to get you to understand there, what I was trying to explain to you is that if you add 60 degrees repeatedly in the degree system, it's the same as adding pi thirds radians. Does that make sense? Because pi thirds and 60 are the same thing. Okay. So this next one you can figure out using the conversion factor or just by thinking about it. So that's negative 180, right? Does that make sense? So, and negative 180 is the same thing as negative pi, right? So what is negative 90 then? If negative half pi, does that make sense? Okay, so negative 90 is negative half pi. Negative 180 is how many negative pi's? Negative 1 pi, yep. So 1/2, 2/2. If I go negative 270, that's up to here, right? Negative 3 pi over 2, which is the same thing as 1.5 pi, right? But nobody ever writes it as 1.5 pi. They always write 3 pi over 2. And then what's negative 360?
Negative 2 pi.
Negative 2 pi.
So does radians work better for going multiple times around?
They both work fine for going multiple times. It's just that almost all math applications use radians. So the definitions of these trig functions that we're going to do come from radians. They're just two different systems, and they both have different, like, you know, things that are good, things that are bad. So just know how to convert between the two of them. Okay. So pi 6, pi thirds, pi halves, 2 pi thirds, 5 pi, 6, and pi. What's happening every single time? What are you adding? It's not as obvious in this one. If you do pi 6 plus pi 6, what's that? A 6 plus a 6 is 2 6, right? And 2 6s 1/3. That's how you got pi over 3. So it's 1 6, 2 6, 3 6, 4 6, 5 6, 6 6.
Red fish, blue fish, 2 fish.
Yeah, it's very Dr. Seussy, yes. Or somebody said, how many degrees are you adding each time? 30. How'd you figure that out?
Had it beat into me.
You had it beat into you? Okay. You could do pi 6 times 180 degrees over pi. That's one way, right? And that is definitely 30. You could also think from the previous example, 60 degrees was equal to pi thirds, right? And so what's half of 60?
30.
And what's-
multiply the denominator by 2.
And half of a third is a sixth, right? That's a lot. There are two ways to think about that. Okay, so if pi 6 is 30 degrees, pi thirds is going to equal 60 degrees because you've added pi 6 to it. Without even thinking that way, what's pi halves going to be? 90, yep. 2 pi thirds will be 120, yep. 5 pi 6 will be 150, right? And what is pi? 180, yep. Okay. All right, let's draw this picture. That is negative pi over 2, right? The same thing as 90 degrees. What's half of 90 degrees? 45. And what's half of a half? 1/4. Okay, so that's why this angle right there is negative pi quarters. So negative pi quarters is the same thing as negative 45 degrees. What's negative pi halves the same thing as?
Negative 90.
Negative 90. Okay, negative 3 pi quarters, it goes past negative 90 an additional how many degrees? So it's minus 90 and then minus 45. So added together, that's how many minus angles?
135.
Minus 135. And then negative pi is same thing as negative 180, right? Okay, these next ones are not going to be pretty. Oops, that was not meant to do. There we go. All right, so 64 degrees. That's not one of the ones we can count out super nicely, right? It's between 0 and 90. So somewhere, the radian measure has to be somewhere between 0 and pi over 2. And as a decimal, pi over 2 is approximately 1.5, right? Because pi is about 3. Does that make sense? Okay. So 64 should be somewhere in between those. So we have to actually, in this case, use the conversion factor. So multiply that by what? Pi over 180, yep. So the exact answer would be 64 pi over 180. And it says to 3 decimal places. So, just get decimal approximation for that.
Do you add in pi?
Yeah, so you do 64 times pi. And you're going to be more accurate if you use the pi button as opposed to like 3.14. Does that make sense? Your pi button has more digits. So tell me.
1.12.
3 decimal places.
1.17.
What was after the 7?
0.
Okay, great. So 1.17, you could say radians if you wanted to. Okay? But if you don't say radians, we'll assume that's what you mean. If you want it to be degrees, you got to put the circle. Okay. We are 108.413. So multiply this by pi over 180. So that will be 108.413 pi over 180.
1.892 radians.
1.892. What was after the 2, just out of curiosity?
1.
Okay. Okay. And the next 2 are just the opposite direction. So we have something in radians and you want to go back 2 degrees. So 0.8, notice there's no label, so that means that it's in radians. So multiply by, you want the radians in the bottom, so what goes in the bottom? Pi. And what goes in the numerator?
180.
180. Okay, so 0.8 times 180, I think was 144 over pi. That's degrees now. And so 2 decimal places, what'd you get?
45.84.
45.84. Does everybody agree that he should round up? And don't forget the degrees symbol if you're in degrees. 45 radians is a lot more than 45 degrees. Does that make sense? Because 2 pi is about 6 point something, right? So 6 radians goes around the circle 1 time versus 6 degrees doesn't go very far in the circle, does it? So there are some problems where you'll have to use a calculator and you've got to make sure that your calculator's in the right mode. This is radian or degree mode, and that's a pretty common mistake, and that'll happen, I think, in chemistry and stuff like that as well. So if you don't know how to change it, ask me after class, and I'll show you how and how to check, okay? All right, 3. It's gonna be awfully close to 180 because 3 is awfully close to pi. Does that make sense? So multiply by 180 over pi and tell me what you get. 171.89. And that is pretty close to, but a little less than 180, right? It should sort of jive and make sense. Okay. So the next thing we're going to talk about just a little bit is how to find angles that are coterminal with other angles. So we want angles in degrees that are between 360 and 720, and the angle needs to be coterminal with 120. So for me, a picture really, really helps. So you have your initial side. 120 is past 90, but not all the way to 180, right? Does that make sense? How much past 90 is 120 degrees? 30. So if this is 90, 120 is just a little bit past that. So what I want you to find is an angle theta that is coterminal with this angle and has a measure that's bigger than 360. So does going backwards give you such an angle?
No.
No. How do you get an angle bigger than 360 in the first place?
It makes a full revolution.
Makes a full revolution and then some more, exactly. So if I make a full revolution, that's a 360, right? Plus another 120. So 360 plus 120, would that fit the bill? That'd be 480. Okay. And that's certainly bigger than 360, so that's, you know, within the number.
Include 360 because it's less than or equal to.
All that is saying is that the angle that you give me as an answer must be in between those values.
Yeah, but isn't 0 conical with 120 because you can go back 120 from where you just went?
Say that again.
Okay, so you start at 360, right?
Yeah.
Don't
Which-
you include that as a conical? Because you can move 360 this way, and then you can go back 360, and then you're back where you were. But you still move 120.
What angle would it be?
360.
So you say 360 is the same thing as 120?
No.
Okay. Then that's what we're looking for are angles that are the same as 120 that are between these values. That's one way. Yep. That'll also, it's not between. You could also have gone around the circle more than once. Does that make sense? So let's see if.
I see now. I thought it was just like intervals of 120. That's what I was thinking.
No. As in the same angle as 120.
Okay.
Yeah. Okay. That makes more sense. Yep. So the question is that is 720 big enough that it would allow going around the circle more than once? Does that make sense? So that would be 360 plus another 360, right? Plus one more 120. Does that make sense? So is 360 times 2 plus 120, what is that going to be? 840. So is that sufficiently small that that's an angle you could count? No. So the only angle that is between those values and is coterminal with 120 is 480. That's the only one. It is possible that if I made that upper number larger, like I made it like 900, then 840 would also be an answer, okay? And negative numbers could be answers if I had let the theta be between, say, negative 360 and 0. I think that's what the next one is. So an angle that's coterminal with 280. So get a rough idea of where 280 is. So this is 90, that's 180. How much is this?
270.
270. So the 280 is just a little bit past that, right? So that's forwards 280 degrees. How much do you have to go backwards to get to that spot? So it's really, you take 280 and you can take away 360, right? So that's negative 80 degrees. Is the same thing as positive 280 degrees. Only difference is how you get there, versus forwards or backwards. Could I have gone negative 80 and then a whole revolution around? I could have, but would that have fallen within the values that I said your theta had to be between?
No.
No. Okay. So that's a couple examples in degrees. Here are a few in radians. So I need an angle between 2 pi and 6 pi that's coterminal with 5 pi quarters. And you've got to figure out where 5 pi quarters is approximately, so you've got an idea of where your angle is. So first of all, is 5 pi quarters bigger than or smaller than pi?
It's bigger.
It's bigger because it's 5 over 4, which is 1.25, right? Okay, so does it make sense also that this is half pi? So halfway is a quarter pi, right? What we're going to do is we're going to count by quarters. This is a quarter, right? This is 2 quarters. This is 3 quarters. That's 4 quarters. Here's 5 quarters. Does that make sense? Okay, so there is 5 pi fourths location. So 2 pi, we need angles that are bigger than 2 pi and less than 6 pi. 2 pi is one rotation around the circle, right? So if I wanted to go to 5 pi quarters, but be bigger than 2 pi, couldn't I just do 2 pi plus 5 pi quarters? That's the same as like adding 360, right? And get a common denominator, because usually these things are given as improper fractions, so that's what, 8 pi quarters? Plus 5 pi quarters, how many pi quarters is that? 13. Okay. So that's going around the circle once, and then the additional 5 pi quarters. We also should check and see if we go around the circle twice, do I still fall within that range? So that would you do, yeah, that'd be 4 pi plus 5 pi quarters, which is what, 16 pi over 4 plus 5 pi fourths, which is 21 pi fourths, right? What you can think is that 21 over 4 is 5.25, so that's still less than 6. Can you go around 3 times? Oh, it's going to be too big. So the point is, adding revolutions in degrees is the same as adding 360, and adding revolutions in radians is like adding 2 pi. It's just equivalent stuff. And I kind of listed them backwards because the next one's actually easier. So negative angles that are coterminal with pi, and they're between negative 4 pi and 0. So this is the angle pi, right? So if I have negative angles, that means I go clockwise, right? Does this negative angle fall within that range? Yes, so one angle would be theta equals negative pi. Could I have done something to the effect of go around the whole way and then go negative again? How many negative pi's is that? Negative 3 pi. Do you see what happened there from negative pi's? You took away 2 pi, right? What would the next number be if you go around backwards twice? Negative 5 pi, but that's too negative, right? Okay, so those are our angles. Okay. So the next page is something that you really, really have to know well. How many of you have seen unit circle before in your life? Yes, did you hate it? Yes. Okay, I'm going to try to help make it a little bit better in terms of being able to know what it looks like, know what the patterns are so you can construct it quickly. One thing that is not a homework assignment but will be on your quiz this week is I'm going to give you a blank one of these and you're going to have to fill it out. Because you just have to, it's like the multiplication tables of trigonometry, you just have to know it. but I'll teach you tricks to remember it because I also struggled with this quite a bit. So the unit circle is a circle of radius 1 that's centered at the origin. It's used to define all these trig functions so we can have angles that are outside the range of the angles that are used in just the basic trigonometry you know. What is an equation of a circle that's centered at the origin of radius 1? You did it this semester. Do you remember?
X squared plus y squared equals.
X squared plus y squared equals 1. Does that make sense? That's the sort of algebraic definition of that equation of that circle. And we're going to use this circle to define 6 trigonometric functions: sine, cosine, tangent, cosecant, secant, and cotangent. And knowing this unit circle is going to help you a lot. So we are going to use these 2 special triangles a lot today. So this first one is called a 45, 45, 90 triangle because 2 angles are 45 and one's a 90. Does that make sense? Does it also make sense that these 2 sides necessarily have to be equal because their opposite angles are equal? Yeah? Okay. So one question I have is if you assume these sides here, because they're equal, just say they're both 1, how do you show that this side is root 2? What do you use? The Pythagorean theorem, yeah. You use 1 squared plus 1 squared equals that c squared, right? And so we've got 2 equals c squared, therefore c equals square root 2, right? That's why that one side is what it is. It's not magic, it's because of the Pythagorean theorem. Now we are going to need a triangle where the hypotenuse is 1. So how could you scale this triangle down so that the hypotenuse is 1? Any idea?
Divide by root 2.
Divide everybody by root 2. So that makes the triangle, it has the same basic shape, it's just going to be a little bit smaller. Still has the same measurements in each of the angles. The hypotenuse is now 1. This side is 1 over root 2. That side is 1 over root 2. And if you rationalize the denominators, what does 1 over root 2 rationalize to? Like multiply by root 2 over 2. Does that make sense? I take 1 over root 2 and multiply by root 2 over root 2, right? Okay. If you did the Pythagorean theorem on those numbers, do you think it would still work? It would. If you do root 2 over 2 squared plus root 2 over 2 squared, it also equals 1. Is everyone clear how that little triangle came from the other triangle? Okay. The other triangle that came up below was a 30, 60, 90 triangle. Have you guys seen that one? Okay. So of these numbers in this triangle, who's the biggest? The root 3 or the 2? 2 is the largest. Root 3 is the second largest, and 1's the smallest, right? Also notice that the smaller number is opposite the smaller angle. Does that make sense? Okay, now the other question is, how do you prove that these sort of numbers are what they are? Is it just magic? And of course the answer is no, it's not magic. But what you do is you say, well, you start with a triangle that is equilateral, right? Every single angle is 60 degrees, okay? Then you drop a perpendicular from one of the angles, which cuts that upper angle in half and makes it 30. And that's why I can say that this side is 1 if that side is 2. Does that make sense? Okay, so the only question then is, how do you figure out that side is root 3? And once again, it's the Pythagorean theorem, right? But if you call this number A, that number is the C, this number is the B, right? You say, well, 1 squared plus B squared has got to equal 2 squared. So B squared equals 3, and therefore B is equal to root 3. But to use this triangle for the trigonometry we're going to do today, I want to scale it down so that the hypotenuse is 1. So what would you divide everybody by here to make the hypotenuse into 1? 2. Divide that by 2, divide that by 2, divide that by 2. And now what the sides are is this hypotenuse is 1, this side's a half, that side's √3/2. Up here is the 30-degree angle, and down there is the 60-degree angle. Okay, so personally I think this makes stuff a little bit easier when you have the hypotenuse being 1. All right, so here is the big unit circle. Okay, so the first thing, this is actually just from Wikipedia, like I took their circle and I deleted all their points and we're gonna just fill them in. So the first thing is, can we fill in all of the degree measures? Does that make sense? Let's do that first. This is 0 degrees. That first angle is 30 degrees. Now look at the red points. There are red points and blue points. Yours didn't copy like that because I don't have a color copier. Does it make sense that the red point is halfway to 90? Okay, so what is the angle at that red point? 45. Okay. So there's 45 degrees. Do you see that with these blue points, that the distance from this axis to that blue dot is the same as the distance from blue dot to blue dot? So if this is 30, that next blue dot's an additional 30, or it's 60. And then the right angle is 90. How many degrees past 90 is the next angle? 30 additional, so that's 120. The next angle is more related to the 45, right? So that's 45 degrees past 90, or 135. You could also observe how far apart 45 and 60 are, right? How far apart are those two? 15, so there's 15 between 120 and 135 also. What's an additional 15 gonna be? 150, right? And then we have 180. What's next? 210, great. And then 225, yep. 2, yep. 300, right? 315 and 330. Okay. Here is everyone okay with the, most people are always okay with the degrees. You hear the degrees? All right. The way to get the radians is to count by quarters and count by 6. That's the easiest way. So we'll do the quarters first. So a quarter of a way around the circle is half of pi, right? So this first one, that first red dot, is pi quarters. Does that make sense? So there's pi quarters. This upper axis is 2 pi quarters or pi halves. So 1 quarter, 2 quarter. What's the next red dot? 3 quarters. Does that make sense? You've got 1/4, 2/4 is a half, right? This next dot is 3/4. You see what I mean by count by quarters? Okay. Where does another pi quarter throw you? Well, this one throws you, one more throws you at pi, which makes 4 pi quarters. But this next one down there is 5 pi quarters. It's 1 pi quarter past pi, right? Then the next axis is 6 pi quarters, but what does 6 over 4 reduce to? 3 over 2, yep. And this is 7 pi quarters. But if you just count 1 quarter, 2 quarter, 3 quarter, 4 quarter, 5 quarter, 6 quarter, 7 quarter, 8 quarter, where's 9 quarters gonna be? 9, right? 10, 10, 11, 12, 13. You can count by quarters and get quarters that are both bigger or smaller. Now the blue points you count by 6. So this first point is 1/6. This next point is 2/6. And how does 2/6 reduce? 1/3. So that next one's pi over 3. And when you use this trick, the important thing is that you don't skip over the axes. Do you see what I'm saying by that? You say, okay, if this is 1/6, this is 2/6, what is this one? 3/6. And you've already got that one done, so you don't have to add it again. This next one's gonna be 4/6. How does 4/6 reduce? 2 pi over 3. Okay. And what's this next point then?
5 pi over 6.
Mm-hmm. And then don't skip this, is the pi is 6 pi over 6, right? Then this one's gonna be
7 pi over 6.
7 pi over 6, yep. This one is 8 pi over 6. How does 8 over 6 reduce? 4 pi over 3. 9 pi over 6. Okay, then how about 10 pi over 6? 10 over 6 would be 5 pi over 3. And then the last one is 11 pi over 6. So if you can carefully count by quarters and count by 6, you can find the angles pretty easily. Okay, is everyone okay with where the angles and radians come from? Is it also clear that you can continue to go around the circle, so you could continue to count by 6 or quarters if you get things that are bigger? Like that's 11 pi 6, there's 12 pi 6, here's 13 pi 6. Okay, so just that's how you would find angles that are, you figure out how many they go around one circle, find the biggest number you can get, and then can count from there. And the other question is, where the heck do these numbers come from, right? So, those are your coordinates, yeah. So this is like, this point, it's like how far over it is and how far up it is. Does that make sense? And if you take this number squared plus that number squared, you're gonna get 1. Does that also make sense? Because you're on a circle whose radius is 1, right? Okay, and so those numbers also come from the triangle that we just did. So here's what I mean. I'm gonna draw it in purple because it's the best color. Okay. Do you see that this is a right triangle? Okay. And how is this triangle related to those points? When you graph a point, you put the x-coordinate first, which is how much is over, right? You put the y-coordinate next, which is how much up, right? So this point is over 3/2, which is the base of this triangle. It's up 1/2, right? Because we're inside of a unit circle, what is the length of this part of the triangle? 1. So that triangle's length is 1. What is this inner angle right there? 30 degrees. Look at that triangle we drew in part B up above. In that triangle you drew in part B, if you have this is 30 and this is 90, what does this side have to be? 60. And because we proved that in a 30, 60, 90 triangle where the hypotenuse is 1, this side's got to be 1/2, right? This side's got to be root 3 over 2. Does that make sense? So that's one place that those numbers come from. There's 1/2, there's root 3 over 2, okay? Now the question is, how the heck does that relate to right triangle trigonometry? So if you go back to SOHCAHTOA, so sine of an angle is the opposite over the hypotenuse. Cosine of the angle is the adjacent over the hypotenuse, right? Using that bitty triangle that I drew right there, what is sine of that angle? Sine would be the opposite side, which is 1/2, over the hypotenuse, which is 1. 1/2 over 1 is 1/2. And the cosine is going to be root 3 over 2, right? Here is the pattern. The x-coordinate, that's always the cosine, and the y-coordinate, that's always the sine. Do you see that? Okay, and this comes from these right triangle things. It's like this next one, the pi quarters. If you drew in that triangle there, that's the 45, 45, 90 triangle, right? If the hypotenuse is 1, what is the length of this side over? Look at the paper on the page before, or just above that. If this hypotenuse is 1 and it's a 45, 45, 90 triangle, how far over is this? Root 2 over 2. And then how far up is it?
Root 2.
And then I ask you the same question, what is sine of 45 degrees? You say, okay, well, here's 45 degrees, right? Sine is the y-coordinate, it's root 2 over 2. Okay? And that comes from this whole SOHCAHTOA definition. And you could do the whole SOHCAHTOA at that angle. You say, okay, well, sine is the opposite over the hypotenuse, it's root 2 over 2 over 1, that's root 2 over 2, right? Okay, this next one, the very last one we'll do, and we'll talk about how to generalize this. You see how that triangle now has a smaller side on its base and a taller side up and down? So that point is how far over?
1/2.
1/2. And how far up?
Root 3 over 2.
Yep. And what angle did that correspond to? 60. So I say, okay, what is cosine of 60 degrees?
That would be 1/2.
1/2. What is sine of 60 degrees?
Root 3 over
Root 3 over 2. Okay. Okay. So in those cases, we could draw triangles. But we can't draw right triangles outside of that range because one of your angles is going to be too big. Does that make sense? So how you generalize the whole sine cosine idea to angles that are too big to be right triangles, you use this pattern that in these points, the x-coordinate is the cosine and the y-coordinate is the sine. So, like for this point down there, what are the coordinates of that point?
0, 1. 1, 0.
1, 0. And if you have 0 degrees, does it make sense that you really have no triangle, right? But you can still talk about sine and cosine there. So what would cosine of 0 degrees be? 1. Sine of 0 degrees would be 0. So you use the right triangle definition gives you that for these numbers, cosine is the x, sine is the y. And then you use that pattern for all the others. Okay? So 1, 0, what are the coordinates of that point? 0, 1. So then I say, okay, what is cosine of 90? Cosine of 90, say, okay, well that's, cosine of 90 is 0, sine of 90 is 1. Okay. Okay, how about this one right there? What are that point's coordinates?
-1, 0.
-1, 0. Okay, and how about this point down there's coordinates?
0, -1.
Okay. And I say find sine of pi. So say, okay, well, pi's over there. Sine is the y, it's 0. Here's one thing that makes your life easier. X is before y in the alphabet, right? These are also alphabetical. Cosine is first, sine is second, okay? Now we'll start this and we'll finish it tomorrow. So how is this point, as far as terms of over and up, related to this point?
1/2 is negative.
The 1/2 is negative, yeah, so that is -1/2 positive root 3 over 2, right?
You just have to follow the coordinate point.
You just have to sort of follow the pattern, like this point right here is sort of the reflective, and this point is the reflection of it over the x-axis, right? So what are those coordinates gonna be?
Negative root 2 over 2 and then root 2 over 2.
Okay, and then how about the last 5 pi 6, what are the coordinates gonna be there?
Negative root 3 over 2.
And positive, okay, great. We can totally finish this. 7 pi 6. That's kind of the same as 5 pi 6, except for it's also below the x-axis, right? So the x is still negative root 3 over 2. It's back the same distance, but now it's also,
Negative.
What will the coordinates be at 5 pi quarters?
Root 2 over 2 over 2 over 2, both negative.
Both negative, yep. How about 4 pi thirds?
Negative 1/2.
Uh-huh.
Negative root 3 over 2.
Okay. 5 pi thirds, will the x be positive or negative?
Positive.
Positive, so it'd be positive,
1/2.
and then
Negative root 3 over 2.
and then positive root 2 over 2, negative root 2 over 2, right?
Yep.
And the last one will be positive root 3 over 2
Minus 1/2.
minus a half. Yep. So if I said find cosine of 7 pi quarters. There's 7 pi quarters, right? Cosine is the first one. I said find sine of 4 pi thirds. There's 4 pi thirds. Sine is the line, right? Okay, so that's how we're going to use this circle, but it all comes from those basic little triangles. Does that make sense? Okay, so I'm going to pause this and pass back your tests. So Charles, let me pause. I'm just going to get a little bit in your way for a second when I pause and save.